Hey, welcome back. In this video we are going to talk about alkene reaction and their synthesis. We are going to dive to the most common reactions of alkenes and the ways how we can synthesize them. So without any further ado, let's dive into them. Okay, let's start first with the synthesis of alkenes. We have two common ways, dehydration or dehydrohalogenation. There are also other ways, but we will see them on the future video. We can start from an alcohol and treat them with a strong acid in the presence of a solvent, DHF tetrahydrofuran, that is this compound here. And we have the formation of alkenes, ethene plus water. As I said in the previous video, in elimination reaction, we have elimination of small molecule, in this case water. Let's move to the second one, dehydrohalogenation, treatment of an halogen with a strong base in the presence of ethanol as a solvent. It's going to give us the alkene plus the remaining products. These are the two common ways to synthesize alkenes. Let's start with the reaction of alkenes. First one, halogenation of alkenes, addition of HX. X represent the halogens. We have here propene, so this double bond here is going to attack the hydrogen here, and this pair is going to move to the bromine, and we are going to have the formation of a secondary carbocation plus bromine. The reason for the formation of secondary carbocation instead of primary carbocation is that secondary carbocation are more stable than primary carbocation due to inductive effect, because secondary carbocation has CH3, 2CH3 in this case, connected, so they give electrons and they stabilize the carbocation instead of primary carbocation that is connected only with one carbon. The addition happens according to Markovnikov rule that states, in addition of HX to an alkene, the hydrogen attaches to the carbon with fewer alkyl substituent, and the X or halogen attaches to the carbon with more alkyl substituent. Okay, keep in mind this rule. So the bromine is going to attack this electrophile here to the carbon, and it's going to form 2-bromopropane. In order to add the iodine that is less reactive than chlorine and bromine, we need to use a catalyst such as phosphoric acid. So the addition here is going to happen according to Markovnikov rule. So the iodine is going to attach to the more substituted carbon. Let's move now to the addition of halogens, chlorine and bromine. Fluorine is too reactive, iodine does not react with most of alkenes. It occurs in anti-stereochemistry. Anti means in the opposite phases of the double bond. So chlorine can be rated like this. So this double bond attracts one chlorine and this one moves away. And chlorine adds here to form a chloronium ion. And this other chlorine that remains here attacked on the opposite side to form a trans product. So 1,2 trans 1,2-dichlorocyclohexane. Formation of this chloronium ion is proved experimentally. Let's move now to the halohydrin formation. It occurs in anti-stereochemistry, so in the opposite phases of the double bond. So first we have the formation of a bromonium ion, like with addition of bromine and chlorine. And after that, so the attack happened like this. After that, we have the addition of water in the opposite side. So the water is going to attack here according to Markovnikov rule. And this bonding pair is going to move to the bromine to stabilize the cation. So what is going to happen? Now another molecule of water is going to take this hydrogen away. This bonding pair is going to stabilize the oxygen. So the final product is a halohydrin formation according to Markovnikov rule. Okay, it occurs in anti. Formation of halohydrins like this on paper is easy, but in the lab it's dangerous because bromine is toxic. So due to the fact that bromine is toxic, we can use another source for bromine, so such as NBS or N-bromosuccinimide in the presence of water, and dimethyl sulfoxide, that again this is another solvent. So we are going to form again halohydrin according to Markovnikov in anti. Okay, this is a simple way, so we can write it shortly NBS. Let's move now to the hydration of alkenes. First method is Oxymercuration Demercuration method that obeys the Markovnikov rules. That means that the OH is going to be placed to the more substituted carbon. So in this case, it's going to be here. So in terms of mechanism, we can first do oxymercuration process. So we are going to have something like this. And after that, water molecule is going to check to the more substituted carbon and move this to stabilize the cation, and we have a formation of a product of an intermediate. And treatment with sodium borohydride gives us demercuration and the formation of this secondary alcohol. Okay? Now, these numbers here, 1 and 2, represent that this reaction goes in two steps, two separated steps. Another way to hydrate the alkenes is by adding the hydroxy group according to Markovnikov rule by using acid catalyzed process. So again here you're going to have the formation of the alcohol to the more substituted carbon according to Markovnikov, also this one. Let's move now to the third way to hydrate an alkene, that is hydroboration method that occurs in syn stereochemistry. Let's take a look at this alkene that is unsymmetrical. So we are going first to add the boron with THF as a solvent, tetrahydrofuran, and the second step is going to be with hydrogen peroxide in the basic medium. Keep in mind, these numbers means that there are two different steps, as I have written below. So the final product is going to be a non-Markovnikov product. I will explain the reason in a moment. So the OH is going to add on this side to the less substituted carbon. The reason for that is that when boron adds, let's say this is like this, hydrogen here and BH2 here, it adds in a syn stereochemistry. And because of the sterical hindrance here on this side, BH2 adds to the less substituted carbon. And due to the hydrogen peroxide, that is an oxidant, is going to oxidize and to yield the final product that is a non-Markovnikov product. So this occurs on the same side, on the same phase. Okay, That's why it's called syn. Up to now, keep in mind that if you want to yield an hydrated alkene that is unsymmetrical, you have to use Oxymercuration, Demercuration to yield a Markovnikov product, so the OH is going to be substituted to the more substituted carbon. And if you want to yield a product that is OH to be to the less substituted carbon, you have to use Hydroboration oxidation. Okay? Keep in mind these two differences. Let's move now to the reduction of alkenes. That is a process that is called hydrogenation, that occurs in syn stereochemistry, or in the same phase, due to the fact that because we are going to deal here with a heterogeneous catalysis. There are two ways to hydrogenate the alkene. So first one is by palladium in charcoal and in ethanol as a solvent, and the other way is by platinum oxide and use acetic acid as a solvent. Both these reactants, the first one is more commonly used, yield a product that is an alkane. So we have removed the double bond, and because it moves in, happens in syn, both hydrogens are added in one side of the double bond. Okay? So keep in mind this one or the second one if you have to do hydrogenation. And keep in mind that occurs in syn. So the two hydrogens add from the same phase due to the fact that we are going to deal with a heterogeneous catalysis. Something to mention here is that alkenes are much more reactive than most other unsaturated functional groups toward catalytic hydrogenation, and the reaction is therefore quite selective. If we do hydrogenation of this ketone here, we are going to preserve the carbonyl group, and we are going to have only the reduction of this double bond here. The same happened to this benzyl ring and also ester. Benzyl ring is not going to be reduced by the hydrogen, is not going to be hydrogenated. It has some specific characteristic that we will discuss later on in the future videos. But we are going to have the reduction only of this double bond here, and the ester group is going to remain the same, untouched. So the product. Also the nitrile group is going to be untouched, only the double bond here. Keep in mind this thing. So alkenes. Okay, I thought to split this video in two parts. So see you in the part 2. Bye.